and power concept also and in torque parallel operation. I will discuss torque as torque angular velocity. By knowing this, and the synchronous torque will try to when there is disturbance in the system, try to restore. There is disturbance. There is synchronizing torque into equal to synchronizing torque into S. So where PSY is the synchronizing torque in newton per electrical radians. Omega s, that is the angular velocity of the rotor, that is omega s is equal to 2 pi ns by 60. Okay, 2 pi ns by 60. So this one is also write it as 2 pi into ns. That is small ns. That is here ns, small ns is the synchronous speed of the machine in revolutions per second, and ns, that is the synchronous speed of the machine in revolutions per minute. Okay. So we know that the synchronizing power per unit displacement in electrical radians will be P suffix S5 is equal to PS by delta delta. So that is equal to 3 into V into ISC. This is the synchronizing power condition for a three-phase system. That is synchronizing power is equal to 3 into V into ISC. So and substitute we get PS is equal to 3 into V into ISC by 2 pi ns, that is Newton meter by electrical radians. So where V is the volts hour per phase and ISC is short circuit per phase. Okay, this is the synchronizing torque, that is 3 into V into ISC by 2 pi ns Newton meter per electrical radians. And coming to the parallel operation of alternators. So in practice, a very large number of three-phase alternators operate in parallel because the various power stations are interconnected through the national grid. Okay, so actually in practice a very large amount of three-phase alternators operate in parallel because the various power stations are interconnected through the national grid. So therefore the output of any single alternator is small compared with the total interconnected capacity. Okay, so the output of any single alternator is small compared with the total interconnected capacity. So for example, the total capacity of the interconnected system may be over 40,000 megawatts, while the capacity of the biggest single alternator may be 500 megawatts. Okay, that means it is fulfilled the above condition, that is output of any single alternator is small. Here it is a 500 megawatts. Compared with the total interconnected capacity, that is 40,000 megawatts. Okay, and advantages of parallel operation of alternators. We have so many advantages. In those things we have taken 4. That is the first one is first advantage is continuity of service. Okay, so continuity of service means if one alternator fails, the continuity of supply can be maintained through the other healthy units. So this will ensure uninterrupted supply to the consumers. Okay, next coming to the efficiency. So alternators operate most efficiently when delivering full load. You already know this one, but units can be added or put off depending upon the load requirement. Okay, units can be added or put off, that means deleted, and that means disconnected depending upon the load requirement. And coming to the maintenance and repair, so it is often desirable to carry out routine maintenance and repair of one or more units. Okay, it is often desirable to carry out routine maintenance and repair of one or more units. And coming to the load growth, so the load demand is increasing due to the increasing use of electrical energy. So you already know this one. So load demand increasing means there is the usage of the electrical energy is also increasing. So the load growth can be met by adding more units without disturbing the original installation. Okay, without disturbing the original installation. These are the advantages of parallel operation of alternators. And next, coming to the conditions for paralleling alternator with infinite bus bars. So, in order to connect an alternator safely to the infinite bus bars, the following conditions are met. So, if you want to connect the alternator safely to the infinite bus bar, the following conditions are met. First one is the terminal voltage. This is also known as RMS value. So, the terminal voltage of the incoming alternator must be same as bus bar voltage. And next one is the frequency of the generated voltage of the incoming alternator must be equal to the bus bar's frequency. And third one, the phase of incoming alternator voltage must be identical with the phase of the bus bar voltage. Okay, the phase of the incoming alternator voltage must be identical with the phase of the bus bar's voltage. In other words, the two voltages must be in phase with each other. Okay, and the phase sequence of voltage of the incoming alternator should be same as that of the bus bar. The phase sequence of the alternate voltage of alternator should be same as that of the bus bars. Okay, these are the conditions for the paralleling alternator with infinite bus bars. Okay, so here I am taking the parallel operation of alternator derivation. So for that one, I am taking two identical alternators. Okay, two identical alternators connected in parallel. So two identical alternators, that is E1 and E2, that is connected in parallel as shown in the diagram. So here I am taking a diagram. It consists of two identical alternators. Those are connected in parallel. Each consists of the EMF value, that is E1 and E2, and it consists of the combination of resistance and inductance, that is also impedance of the first alternator, that is Z1, and same combination is given to the second alternator. This is also known as Z2. That is the synchronous impedance or impedance of the alternator 2, and it circulates a current, that is ISA, that is the synchronizing current, and it consists of the current I1, and the alternator 1 consists of the I1 current, and alternator 2 consists of the I2 current, and it also consists of the total current, that is I, and it consists of a load, and these two alternators connected to the load, and it consists of the terminal voltage, that is V, or load voltage V. Okay, by using this diagram, we have to derive the parallel operation of alternators. Okay, so coming to this one, so here I am assuming cylindrical rotor type alternator. Okay, so from that one I am writing the terminal voltage. So the terminal voltage of the cylindrical rotor type alternator V is V bar is equal to E1 bar minus I1 into Z1 bar, I1 bar into Z1 bar. So that is equal to E2 bar minus I2 bar into Z2 bar. So here the terminal voltage is equal to both the alternator equations, that is V bar is equal to E1 bar minus I1 bar into Z1 bar is equal to E2 bar minus I2 bar into Z2 bar. And from this diagram, load current I bar is equal to summation of both the currents in the alternators, two alternators, that is I1 bar plus I2 bar. So from the above expression, we will write the E1 bar is equal to V bar plus I1 bar into Z1 bar. So here the terminal voltage V bar is equal to I bar into Z bar. So from this I am writing E1 bar is equal to V bar plus I1 bar into Z1 bar. So in the V bar place I am substituting I bar into Z bar. So that is E1 bar is equal to I bar into Z bar plus I1 bar into Z1 bar. And next we know that the load current I is equal to I bar is equal to I1 bar plus I2 bar, and substitute that equation here. So that is E1 bar is equal to I1 bar plus I2 bar of Z bar plus I1 bar into Z1 bar. So from this one I am taking common of I1 bar, that is I1 bar of Z plus Z1 bar plus I2 bar into Z bar. This is treated as first equation, that is E1 bar is equal to I1 bar of Z bar plus Z1 bar plus I2 bar into Z bar. This is the first equation. And next also from the equation, that is E2 bar is equal to V bar plus I2 bar into Z2 bar, and here also I am substituting in the V bar plus I bar into Z bar. So that is there is a mistake is there, that is not E1 bar, it is the E2 bar. Okay, please correct this one. So E2 bar is equal to I bar into Z bar plus I2 bar into Z2 bar, and E1 bar is equal to, in the I bar place I am substituting I1 bar plus I2 bar. So now the equation becomes I1 bar plus I2 bar of Z bar plus I2 bar into Z2 bar, and lastly we have E2 bar is equal to I2 bar of, here I am taking the common term, that is I2 bar. We have I2 bar of Z bar plus Z2 bar plus I1 bar into Z bar. So treat this equation as equation number 2, and solving equation number 1 and second equation, that is we have I1 bar is equal to E1 bar minus E2 bar of Z bar plus E1 bar into Z2 bar by Z bar of Z1 bar plus Z2 bar plus Z1 bar into Z2 bar, and similarly I2 bar is equal to E2 bar minus E1 bar of Z bar plus E2 into Z1 bar by Z bar of Z1 bar plus Z2 bar plus Z1 bar of Z2 bar. These are the two currents we have by solving the E1 bar and E2 bar equations. Okay. Next, from this one, the load current I bar is equal to I1 bar plus I2 bar. Okay. So from this one, I am taking the I bar is equal to E1 bar into Z1. I am substituting I1 and I2 values here. So it will become E1 bar into Z1 Z bar minus E2 bar of Z bar plus E1 Z2 bar plus E2 Z2 bar minus E1 Z bar plus E2 Z1 bar by Z bar of Z1 bar plus Z2 bar plus Z1 bar into Z2 bar. So finally we have the I bar is equal to E1 bar into Z2 bar plus E2 bar into Z1 bar by Z bar of Z1 plus Z2 bar plus Z1 bar into Z2 bar. So from this one I am writing I bar is equal to E1 Z2 bar plus E2 Z2 bar Z21 bar by. So here I am common the term Z bar, and we have Z1 bar plus Z2 bar plus Z1 Z2 bar by Z bar. So we know terminal voltage V bar is equal to I bar into Z bar. So here I am substituting in the I bar place the above equation, that is V bar is equal to, in the I bar place I am substituting E1 bar into Z2 bar plus E2 bar into Z1 bar by Z bar of Z1 bar plus Z2 bar plus Z1 bar Z2 bar by Z bar whole into Z bar, whole into Z bar. So after simplifying this one, we have E1 Z2 bar plus E2 Z1 bar by Z1 bar plus Z2 bar plus Z1 Z2 bar by Z bar. So this is the voltage equation of an alternator in the parallel operation. And up to now we discussed the parallel operation of alternators and derivation of the parallel operation of alternators. And next, coming to synchronization of alternators. Synchronization of alternators. So before going to this one, we have some information about the synchronization of alternators. That is, in the last decade, there were tremendous advances in civilization which resulted in more per capita consumption of electricity. So to meet this ever-growing demand for electricity, it is necessary to use more number of alternators connected in parallel to a common grid. So before connecting the alternators in parallel, the two machines connected in parallel must satisfy the following conditions. So that is, first one is the frequency of two alternators must be the same, and the voltage of two alternators must be the same, and third one, the phase sequence of two alternators must be the same. These are the conditions we have to satisfy before connecting the alternators in parallel. Okay, and the two machines connected in parallel must satisfy these conditions. Okay. Next, so when one alternator is to be connected to n infinite bus, so the conditions mentioned above, that is the three conditions of the alternators, should match with those of the infinite bus bar. So those conditions will have to satisfy the infinite bus bar conditions also. That means both are should match. So this is called the synchronization. Okay. So one alternator is to be connected to infinite bus. The conditions mentioned above of the alternator should match the infinite bus bar conditions. Then it is called synchronization. So a circuit for synchronizing an alternator to an infinite bus bar is shown in the diagram. I will show the diagram later. Okay. So this is the diagram we are taking. Okay, for example, so a circuit for synchronizing an alternator to an infinite bus bars is shown in the diagram. So in that one we have the alternator. The alternator is connected to the bus bars through a synchronizing switch S. So here we have the alternator. Okay, here we have the alternator, and this alternator is connected to the bus bars through a synchronizing switch S. Synchronizing switch S. So this one. Okay, next two voltmeters are connection either side of the switch. Here I am connecting two voltmeters, V1 and V2. Okay, so two voltmeters are connection either side of the switch. So after ensuring the conditions mentioned above, for synchronization, the switch S is closed. So after satisfying the three conditions mentioned above for synchronization, after that the switch S is closed. Up to that, the switch is in open condition. After satisfying those conditions, the switch is closed. So this can be realized as explained below. So I will explain this one in a detailed manner. So here I am taking a alternator, and this alternator is connected to the three-phase infinite bus bar through a switch S, and this alternator consists of three-phase connection. That means the three-phase terminals R, Y, and B. It consists of the stator, three-phase stator, and it is coupled to DC motor, and it also consists of three lamps. One is here we have the three lamps LLL we have, and two voltmeters V1 and V2, and ammeter A, and it has a separate connection of the this one. It consists of the DC supply 220 volts, and DC supply is connected to the external connection through a switch, DBS switch, and it consists of a rheostat, and it also consists of a ammeter to measure the field current, and it also consists of the field winding. The field winding is connected to the ammeter. That's why we are measuring the field current from this one. So this is the circuit arrangement for the explanation of the synchronization of alternators. Okay, so firstly, the speed of the alternator is first adjusted to a suitable value which corresponds to the frequency of the busbar voltage by controlling the speed of the DC motor. So firstly, I am adjusting the speed of the alternator to a suitable value, that is normally 1500 RPM. That corresponds to the frequency of the busbar voltage by controlling the speed of the DC motor. Next, the alternator voltage is read by the voltmeter V1 is made equal to the busbar voltage as read by the voltmeter V2. So here the alternator voltage V1 is equal to the busbar voltage V2 by varying the alternator field current IF, by using the field rheostat. Okay, so under these conditions, when two voltages are equal, that is alternator voltage and busbar voltage, the three lamps connected across the synchronizing switch S. So in the diagram, three lamps are connected across the synchronizing switch S will become alternately dark. So, and bright, dark and bright, that a frequency corresponding to the difference between the frequencies of the two voltage sources, namely that of the alternator EMF and voltage of the infinite bus bar, all are same. So when the difference between the two frequencies is very small or zero, the bulbs will go completely dark. Okay, and this can be done by adjusting the speed of the alternators through prime movers. This is condition for synchronization. Okay, so this can be done by adjusting the speed of the alternate through prime movers. So the prime mover is used to drive the alternator at synchronous speed or constant speed. So this is the condition for synchronization, but under certain conditions, all the three lamps will not simultaneously become bright or dark. Okay, but under certain conditions, all the three lamps will not simultaneously become bright or dark. So this is possible only when the phase sequence of the alternator and the busbar voltages is not the same. Okay, this is possible only when the phase sequence of the alternator and the busbar voltages is not same. That means under certain conditions, all the three lamps will not simultaneously become bright or dark. Those conditions are only when the phase sequence of the alternator and the bus bar voltages is not same. If these voltages or phase sequences are same, means the lamps are simultaneously become bright or dark. Okay. So then the two voltages are not in synchronization, and this can be corrected by interchanging any two lines of the three-phase supply, either RY or YB or RB or RY supply on the of the three-phase supply on the alternator side. Okay, so when the phase sequence on both sides is the same, okay, when the phase sequence on both sides is the same, and if the two voltmeter indicates the same reading, okay, so when the phase sequence on both sides is same, so the two voltmeters indicates the same reading. That means alternator voltage is equal to the infinite bus bar voltage. Okay. So all the bulbs will simultaneously become dark. So which corresponds to the instant that the two voltage supplies are synchronized and the switch S can be closed. Okay, the two voltage supplies are synchronized. That means infinite bus bar voltage and alternator voltage. Both are synchronized and the switch S can be closed. Synchronized means it is equal. Okay, this method of synchronization is called dark lamp method. This is one of the method to prove the synchronization in an alternator. And now the alternator is ready to share the load. So after completion of this, the alternator is ready to share the load. And the load on alternator can be put down by advancing the rotor with respect to the stator field by slightly increasing its speed by 2 to 5 rpm. So the load on the alternator can be put down by advancing the rotor with respect to the stator field by slightly increasing the speed by 2 to 5 rpm. Like this we are changing the speed of the alternator after completion of that desynchronization condition. Okay, and now coming to the methods of synchronization. So the method of connecting an incoming alternator safely to the live bus bars is called synchronizing. So the method of connecting an incoming alternator safely to the live bus bars is called synchronizing. That means the equality of voltage between the incoming alternator and the bus bars can be easily checked by a voltmeter. So I already said these things in the previous concepts. Okay, next the phase sequence of the alternator and the bus bars can be checked by a phase sequence indicator. Okay, so here we are using one phase sequence indicator, so that will indicate the phase sequence of alternator and bus bars can be equal, and difference in frequency and phase of the voltages of the incoming alternator and bus bars can be checked by one of the following two methods, that is 3-lamp method. It is also called as one dark two bright method, and by Synchroscope method. These are the two methods which is used to help the synchronization in an alternator. So I already discussed the first one, that is 3-lamp method in the previous concept in the synchronization in alternators, and here also I am explaining the same thing. Okay, that is first one is 3-lamp method. So in this method of synchronizing, 3 lamps, namely L1, L2 and L3 are connected as shown in the figure. So this is the diagram, first diagram. On the left side of the diagram, we have the connection. So here I am taking the incoming alternator. So it connects, the incoming alternator is connected to the bus bar through 3 lamps and 3 switches, and it consists of the phases R1, Y1, B1 and R2, Y2 and B2 and lamps L1, L2, L3. Okay, that means, so the lamp L1, so if you observe this diagram, the lamp L1 is straight connected. So this one, the lamp L1 is straight connected to the, which one? L1 is straight connected between the corresponding phases, that is R1 and R2. So this one. So the infinite bus bar, this is R1, Y1, B1. So here the lamp L1 is connected straight across the terminals R1 and R2. R1 and R2. And the other two are cross connected between the other two phases, the other two, L2 and L3. So L2 is connected to the terminal Y2 and Y1, and L3 is connected between B1 and B2 like this, and thus lamp L2 is connected between, the lamp L2 is connected between which one? So the lamp L2 is connected between Y1 and B2, and lamp L3 is between B1 and Y2. So Y1 and B2. So Y1 and B2 and L3 is B2, sorry, B1 and Y2. Like that the lamps are connected, and when the frequency and phase of the voltage of the incoming alternator is the same, so when the frequency and phase of the voltage of the incoming alternator is the same as that of the bus bars, the straight connected lamp L1 will be dark. The straight connected L1, that is, it is connected between the phases R1 and R2. The lamp L1 will be dark, while cross connected L2 and L3 will be equally bright. So the lamp L1 is fully dark, and the lamps L2 and L3, which is connected crossly, those are shine like bright. So at this instant, the synchronization is perfect, and the switch of the incoming alternator can be closed to connect it to the bus bars. Okay. And at this instant, the synchronization is perfect, and the switch of the incoming alternator can be closed. Okay, here we have the switches. So after meeting the synchronization conditions, the switch of the incoming alternator can be closed to connect to the bus bars. So here uh, one phasor diagram is there to explain this three lamp method. So here we have the totally 6 phases. Those 6 are, one is for the 3 is for the incoming alternator, and another 3 is for the infinite bus bars R1, Y1, B1 and R2, Y2, B2. Okay, so the phase difference between these phases is 120 degrees. Okay, so in figure B there is a phasor diagram. The phasors R1, Y1, B1 represent the bus bar voltages. There is infinite bus bar, the thick lines, and phasors R2, Y2, B2 represents the voltages of the incoming alternator. So here we have the phasor diagram. So here R1, Y1, B1 lines are for the incoming, infinite bus bars, and the dotted lines phases are R2, Y2 and B2 are the incoming alternator phases. Okay. Next, at the instant when R1 is in phase with R2, okay, that means voltage across lamp L1 is 0. That is directly connection R1 and R2, and voltage across lamps L2 and L3 are equal. So L1 lamp is 0, voltage is 0, and voltage across the lamps L2 and L3 are equal. And therefore, the lamp L1 is dark, while L2 and L3 will be equally bright. So at this instant, the switch of the incoming alternator can be closed. Okay, thus incoming alternator gets connected in parallel with the bus bar. Okay, the switch of the incoming alternator closed. Thus incoming alternator gets connected in parallel with the bus bars. And coming to the last method of the synchronization, that is synchroscope method. So here a synchroscope is an instrument. So synchroscope is an instrument that indicates by means of a revolving pointer. Okay, here we have one pointer. It is in circular shape, and it have the pointer. Okay, that pointer gives the phase difference and frequency difference between the voltages of the incoming alternator and the bus bars. Okay, so this is the diagram. So here we have the circular shape. In the circular shape we have one indicator. So it will show two sides, one is slow and one the faster. If we turns left to left side, it gives the slow, and it moves to the right side, it gives the fast. And it consists of the infinite bus bars and an incoming alternator. So the incoming bus bars consists of the infinite bus bars consists of the phases R and Y and B, and the incoming alternator consists of the phases R dash, Y dash and B dash. Okay, so here it is essentially a small motor. So this synchroscope is essentially a small motor, and the field being supplied from the bus bars through a potential transformer and the rotor from the incoming alternator. So the field being supplied from the bus bars, that is R, Y, okay, and through a potential transformer. So here we are using a potential transformer, okay, and the rotor from the incoming alternator. So rotor also we are using from the incoming alternator. Okay, so here a pointer is attached to the rotor. So here a pointer is attached to the rotor. So this one. So when the incoming alternator is running fast, the rotor and hence the prime pointer moves in the clockwise direction. Okay, it moves in the clockwise direction. That is, it is moved to the right side. Okay, that is the clockwise direction. And like that, we have to meet these conditions. So here we have to satisfy the three conditions. That is, voltage in the incoming alternator and busbar alternator is equal, and EMFs are also equal, and phase sequence are also equal. After satisfying those things, we have to connect the alternator to the infinite busbar. Okay, like this we are taking the synchroscope method and 3-lamp method to discuss. Okay, thank you for watching this video. In the next class, I'm going to discuss uh, uh, and another methods or another concepts. Okay, thank you.